Hey team, you ready for video number 9 for our acid-base journey? Again, lots of review, but not for this problem. This is what I call a doozer. I would love to see this kind of problem. Oh, I got a hair up there. I would love to see this kind of problem. Big hint, capital H, on your next exam. This involves a whole lot of concepts on here. Seems simple. You look at this problem and you go, that looks pretty easy, right? So we're going to look at the pH of salt solutions. So look at the last video we did that talks about ions, cations and anions, and whether those can be neutral, weak acids, or weak bases in water, looking at that acid-base table. So we've got a potassium cyanide solution. I give you the molarity. It's a 0.024 molar solution of potassium cyanide. Simple question. What's the pH? All right, we're going to fill up quite a few boards on this one. So as I'm doing this video as a complete separate video to calculate it, but pretty much everything we've been learning falls into this one problem. I love it. I love these comprehensive problems. Very first thing we need to do is take a look and recognize that that's an ionic compound. It's a soluble salt, so it's going to dissolve 100% in water, undergo hydrolysis, aka dissociation. So let's write the dissociation equation for that. Take a look at the cation, take a look at the anion, and see whether those have acidic or basic behavior or whether they're neutral. I would very much like for you, yes, you, to pause this and do that for me real quick. Tell me whether the cation's acidic, basic, or neutral. Tell me whether the anion is acidic, basic, or neutral as well. Pop that on the board there. Let me go ahead and do it. So we've got potassium cyanide. That is going to undergo 100% dissociation in water to give us the potassium cation. And the cyanide, ooh, I'm sure you've heard of that one, the cyanide anion. I'm going to analyze these, and I'm going to look at the potassium. Now, the potassium ion is the cation from a strong base, potassium hydroxide. And so since that comes from a strong base, that potassium ion is going to be neutral. That will not have any acidic or basic behavior. It is too weak to ionize in water. Now, the cyanide ion's probably not going to be neutral because otherwise this would be a stupid problem, right? If they're both neutral, then all you have is water, which auto-ionizes and creates a pH of 7, right? Those are pretty simple. But let's look at cyanide. If that comes from an acid, that acid would be HCN, okay? And so I'm going to take a look at my little acid-base table. Look for the cyanide ion or HCN. So if you look over here, you can see HCN and its conjugate base cyanide right on. So HCN is a weak acid, right? It's in the weak acid category. So its conjugate base, the cyanide ion, is below water. All right, so any base, it gets stronger for bases going down, any base below water is going to be strong enough to ionize in water. So this doesn't give me the Kb value though. Cyanide ion is going to react with water. So this will be weakly basic. I'll just put weak base. So I know that since this is neutral and that's a weak base, the pH of this potassium cyanide solution is going to be greater than 7. All right, so it's got to be greater because we got a weak base, so that's going to be greater than 7. So let's attack this problem. What I want you to do now, before we get started on our ice tables and whatnot, I want you to take a look at this, and we need 2 pieces of information before we begin. Remember, normally we're going to do the Q versus K, the ice table, the Kb expression, all that fun stuff. I want you to tell me what we need the concentration of that cyanide ion is. I gave the concentration of this, but what's the concentration of this? And then I want you to look up the Kb value for that. Go do that for me real quick. Be right back. All right, sorry, I got distracted there listening to some 3 Days Grace. And if you hear some little tinkling in the background, That is my children practicing their piano. Never dull. All right, I asked you to do two things. Get me the concentration of the cyanide ion and its Kb value. And if you noticed, that's not on the Kb table. Oh no, what are we gonna do? Here we go. I know that this is 100% ionized, so that the cyanide ion concentration should equal the original potassium cyanide, which is 0.0424 molar. So it's kind of a preliminary stuff we got to do before we get to the steps for equilibrium problems. Now we need the Kb value for that. Ooh, all right. Let's see what we got here. Kb. Let's write the ionization equation for that real quick. So I'm going to bring the cyanide ion down. Sound effects optional. So the cyanide ion is going to function as a weak base in water. So that is going to be taking an H plus away, giving us HCN. Plus that loses an H plus, we get the hydroxide ion. So that's the equation of interest, right? You don't even need the dissociation equation. You can do that in your head. This is the equation of interest. The cyanide ions acting as a weak base. So let's calculate the Kb value for this bad daddy, all right? Kb, and again, if you look for it, let me find my Kb table. Oh, mommy. So here's my Kb table again. There is no cyanide ion on there. No! What are we going to do? So we need to use the Ka, Kb, multiply those together, gives you Kw. So we know that Kw is Ka times Kb. And we are after the Kb for this. So let's bring that down. So Kb for the cyanide ion will be Ka. We just did this on the last video twice. That will be Kw over Ka of the conjugate, right? Here's the conjugate acid of the cyanide. So this will be the Ka for the HCN, which we should be able to find on our Ka table. So Kw, which will be provided for you for exams, is 1.0 times 10 to the minus 14. Let's look up the Ka value for HCN. Oh, please be on there. Please, please, please. Let me find my Ka table. Now, for quizzes and exams, I'll provide you these all the time. For your homeworks and stuff, you'll have to look these up. Let's see. HCN, hydrocyanic acid. Woo! Looking down, looking down, looking down. There's some hydro. Where'd it go? Hydro, looking upside down here. Hydrocyanic acid. There's my HCN. Looks like 6.2 times 10 to the minus 10. So let's put 6.2 times 10 to the minus 10 there. Two significant digits for each, and I get 1.612. 1.6, good to two sig figs. 1, 2 times 10 to the negative fifth. That is our missing Kb value. So preliminary stuff, we've identified our weakly basic ion in that salt solution. The other one being neutral. We know its concentration. We know its Kb value now. So now we can do our Q versus K in step 1, see which way this shifts. At equilibrium, pretty obvious, it's going to be shifting to the right. We have no products in this scenario. And then do our ice table, set up our Kb expression, solve for x. And from the value of x, we'll be able to get the pH of the solution. So let me erase this board. See if you can do the Q versus K for me for this reaction, this equation right here. And if you're feeling highly motivated today, right, you've had your caffeine or whatever, you can work ahead, do the ice table, do this whole problem, and see if you can solve it before I do. I would be very much impressed. All right, did you do it? Did you do it? Did you do it? Here, all I did is rewrote our equilibrium equation here, set up a blank ice table. But before we can do the ice table, we've got to do the Q versus K. So in equilibrium type 3 problems, do Q versus K, ice table, K expression, solve for X, and then in the last step, figure out what you got to do with X, whatever, I could have asked for equilibrium concentrations, percent ionization, pH, whatever. All right, let's do our Q versus K. So if I set this up, Q will be the products initially times the OH minus over the CN minus. And initially I gave you 0.024 molar of that. Water we don't have to worry about. And since we're starting with the CN minus, right, we have the potassium cyanide solution. That undergoes dissociation, forming the potassium ion and the cyanide ion. Then the cyanide ion ionizes in water. So we're starting with none of these products over here. We can plug those values in. So we're going to get 0 times 0 over 0.024. Of course, this is the type of Q you could have done in your head. You don't have to show me that stupid math. That happens so often. Obviously 0, even though our KB value is pretty small. 0 is smaller, I think. So this will be less than KB. Therefore, this is going to shift to the right. To the right. Obviously, there's no products. It's going to shift to the right. So step 1's kind of a simple little one on an exam. You can do step 1 in a couple seconds. Just go, hey, there's no products. It's going to shift to the right, or Q0 is less than K, shift right, boom, done. Move on to the ice table. And the ice table you can do in a couple seconds as well. These seem like daunting problems, but man, you can really fly through these. Here we go. Let's fill this in. We are shifting this way, so my reactants are going to be negative. My products are going to be positive. They all have coefficients of 1, so I'm going to lose X of my reactant when the cyanide ion ionizes over. I'm going to form X of the HCN and form X of the OH minus. The equilibrium, let's add those together. So this will be 0.024 minus X. That will be my equilibrium concentration for my cyanide ion, what it started with, minus whatever we lost when it ionized and react with water. Since I started with nothing for the HCN, it'll be 0 plus X, or just X. I started with nothing for the hydroxide ion, so 0 plus X gives me X. Step 1 and 2, they should be cakewalk for you guys at this point in time. All right, here we go. Now, let's do step 3. Let's set up our K expression. So KB will be, and now again, it's exactly like the reaction quotient. It's just we're not going to use initial conditions. We're going to use equilibrium conditions, which we don't know. So we're going to put those in terms of X. Let's see, that's going to be the concentration of HCN raised to the power of 1 times the hydroxide raised to the power of 1. Divided by the cyanide, also raised to the power of 1. Everything's got a stoichiometric coefficient of 1. We're going to plug in X for my HCN equilibrium concentration. We're going to plug in X for my hydroxide ion equilibrium concentration. Just pulling it, extract it from the ice table. That's why ice tables are so nice. The CN minus will be the initial 0.024 minus however much ionizes X. Let's make always make your simplifying assumption to avoid the quadratic equation, or in one of your homework problems, you end up getting an X cubed term. You can't even use the quadratic equation. You have to use the method of successive approximations. I'm never going to make you do that. Just once on the homework to see how horrific that is. You can look that up in the appendix. I'm not going to teach it. All right, let's simplify this. I'm going to make the assumption that X is so small that 0.024 minus X is 0.024. So let's multiply these two X's together to get X squared in the numerator. And I'm just going to leave that as 0.024 in the denominator. This will really make it easy so we can avoid the quadratic equation. I think the last two examples I made you use the quadratic equation. I think I'm nice on this one. Let's hope. If this creates less than 5% error, and again, 2 ways you can test this assumption validity. You can just go through and solve for X, take X divided by 0.024, times that by 100, and if that's less than 5%, this is valid. Or we can do the shortcut and figure out if it's a valid assumption before we solve for X, which I personally like to do, where you take the molarity of that species, in this case the base, and divide it by the Kb. So let's do the assumption validity test. Let's test the assumption. I will always designate 1 point on a quiz or an exam for the assumption validity test, right? So if you don't do it, you just assume it's valid and don't prove it, I'm going to ding you a point, right? If you do it, I'll give you a point. You have to prove it's valid. If it's not valid, you can't do it. You have to use the quadratic, right? Got to prove it to me. It's pretty easy to do. So that is going to be the molarity of the base divided by Kb. Remember that shortcut I taught you earlier? If it's an acid, it'd be the molarity of the acid divided by Ka. If that's bigger than 100, this is totally valid. So what was the molarity? That was 0.024. What was our Kb value? I have forgotten what our Kb value was. 1.612. Good to two significant figures times 10 to the minus 5. Two significant digits in both. So if I divide those, I get 1,488. Good to two sig figs. I would say that that's greater than 100. Right? A little too close for my liking, but it's greater than 100. So this should create less than 5% error. And our assumption is valid. Yes, and I am now out of board space. I'm used to these gigantic double screen boards in our lecture hall. Now I got this little dinky whiteboard I found in my garage. Right? Make do. We're all in this same situation together with these cuckoo times. So make do with what you got and just have some fun with it, right? I'm going to pause this, erase the board. But we know this assumption's valid, so while I'm erasing this board and putting up the next part, I want you to solve for x for me. And given that value of x, extract the information, what is x, and see if you can get the pH of the solution. I'll be right back. All right, my friends. Did you get the same value of x that I got for this? Fairly simple math because the assumption worked. So what I did is I rewrote this. So the Kb is equal to x squared over 0.024 after proving that assumption was valid, right? So I got to isolate x. So let's move the 0.024 over. So I'm going to take x squared is equal to Kb times 0.024. I just moved that 0.024 to the other side. Then I take the square root of both sides. So the square root of x is x. The square root of that would be there. Then I'm going to plug in my value of Kb that we solved for early on. So 1.612 times 10 to the minus 5th, good to two significant digits, times 0.024, which was the initial concentration of the cyanide. Take the square root of that whole enchilada, and I get 6.219 times 10 to the minus 4th molar. That's good to two significant figures. So that is x. So what you need to do is look back on your equilibrium table and be very careful where you tread right now. This is a huge, if not the biggest mistake students make on this kind of problem, is they misidentify what x represents. So a lot of people, a lot of students would just take that value and automatically assume that's my hydronium ion concentration, and then take the negative log of that to get the pH, which would be wrong. That would give you a pH less than 7. Remember? Now this, to tell you the truth, that's what I did when I did this problem the first time. Oh, I got my own problem wrong because I was in a hurry and I just blatantly just assumed that X was hydronium. I took the negative log of that and got a pH in the 3 range. And I thought about that. I'm like, wait a minute, this is a weak base, right? We thought about that before we started the problem. Cyanide ion is a weak base. So we should get a basic solution which should have a pH greater than 7. And my answer was a pH of 3 something. I'm like, that doesn't sound right. Bases don't give pHs less than 7, especially around 3. So what did I do wrong? It's because I rushed it right here. I made the same mistake. So if the professor makes it, you should watch out for it. X, if you look on the ice table, X is your hydroxide ion concentration. So that is equal to 6.219 times 10 to the minus 4th molar. That's a pretty ugly molar there. big mistake students make is making that assumption. So if I take the negative log, so there's two ways you can do it. I took the negative log of this to get the POH and then subtracted that from 14 to get the pH. Or if you look at the pH square, right, I could take the OH minus, go to H through O plus, and then take the negative log of that to get pH. So two ways you can attack this problem. I'm just going to take the negative log of that. So POH will be the negative log of the OH minus concentration, which is X here. So let's take the negative log of 6.219 times 10 to the minus 4th molar. Whoop, I don't even need the molar there. With a vertical dashed line between the 2 and the 1, giving us 2 significant digits in our concentration. Since I'm doing a logarithm, the number of significant digits in the concentration will give me the number of decimal places in my answer. So my POH, what did I get? 3.2062. 3.2062. So when I first did that problem, I just circled that and said I was done. Oh, I thought that was the pH. It's not. It's the POH. Now I just subtract that from 14 to get the pH. If you recall, pH plus POH is 14.00. I derived that for you when we were looking at the pH review quite a while ago, several videos ago. But as long as you have the POH, you can get the pH to subtract it from 14. And vice versa. I can get the POH by subtracting 14, doing 14 minus the POH. Let's do it. So pH will be 14.00 minus the POH. So I'm going to get 14.00 minus this non-rounded value here. Always use the non-rounded value. Notice I don't round anything, nothing. I round absolutely diddly squat until I get to the answer that was asked for in the problem, which was, what's the pH of this 0.024 molar potassium cyanide solution? All this time later, we're finally here. I'm subtracting, so I'm limited by largest absolute uncertainty. Where's my purple pen? There it is. Or fewest decimal places. So I got two decimals. I'm going to get 2 decimal places in my answer. So I get a pH of 10.79, vertical dash line, doing the non-rounded or intermediate value, with a 3.8 after it. So this is closer to 10.79 than 10.80. I am not going to round that up, so that stays as 10.79. That's a very satisfying problem right there. Now this makes sense. Remember, we predicted the cyanide ion was weakly basic, so the pH should be greater than 7. So that makes a whole heck of a lot of sense. Awesome problem, guys. Know how to do this, and you're going to be kicking butt on my quizzes and tests. You rock! We'll see you for the next video.